Hello everyone, welcome to another Quad Education Test Prep Fundamentals video. My name is Tom and today we're going to talk about a classic topic that comes up a lot in both the SAT and ACT. That topic is special triangles. Alright, let's take a look. There are 4 special right triangles that both the SAT and ACT include in their math curricula. The SAT gives you 2 of them in the little equation bank at the beginning of each math section, but you really should just know these anyway, because if you're having to look back at that equation bank, then you're not using your time as effectively as you should. So first, let's define these 4 triangles. I'd like to separate them into 2 subcategories. The first, triangles with nice sides, or Pythagorean triples, and triangles with nice angles. Because as far as I can tell, those 2 identities are mutually exclusive. You can't have both nice sides and nice angles. First, looking at the triangles with nice sides, if you want to be proper, these are called Pythagorean triples because they have integer sides that satisfy the Pythagorean equation. The first one is far and away the most frequently occurring triangle in both of the tests, and that is the 3-4-5 ratio triangle. Because 3 squared plus 4 squared does indeed equal 5 squared. And big important note here, this ratio, 3 to 4 to 5, does not need to be the exact numbers 3, 4, and 5. So if this number was 6 and 8 and 10, which is to say 3 times 2, 4 times 2, and 5 times 2, that is the same thing. That is the same ratio between the sides. Similarly, you could see 9, 12, 15, and even 6,000, 8,000, 10,000. It's something as high as that I have seen. So do bear that in mind. They like to sneak these in and hide them in really interesting places, but you always want to be on the lookout for it because it's a really good way to skip having to do Pythagorean equations. Next, we'll look at the 5, 12, 13 triangle. What I said about different multiples of this ratio appearing on the test is also true, so you may see a 5, 12, 13 or a 10, 24, 26 triangle. Okay, now moving on from triangles with nice sides to triangles with nice angles, let's look first at the 45, 45, 90 triangle. What we do here is draw a square with length of side x, as I've done, and we will cut it in half diagonally to create a triangle. And now that we have a right angle, what we'd like to do is calculate the hypotenuse using Pythagoras. So you can just do that to the left here. A squared plus b squared equals c squared. We know what a and b are. They're both x. And we don't know the hypotenuse. Now, x squared plus x squared, there's 2 of them, is 2x squareds. And that's equal to c squared. And to get the square off, we can just square root both sides. So c is equal to the square root of x squared is just x, and the square root of 2 will leave as the square root of 2, which shows us that this is going to be x times the square root of 2 for the hypotenuse here. It's important to note that this isn't always a letter. So for example, if the length of side for this square was 5, and we'd have 5, and then 5, and then 5 square root 2, or if it was 13, 13, and then 13, and 13 root 2. So next we'll move on to the 30, 60, 90 triangle here to the right. So what this is an equilateral triangle, and you can feel free to argue about pronunciation among yourselves in the comments, but we have an equilateral triangle, and what we'll do is draw an altitude to cut this in half or bisect it. So the length of side I've indicated here is 2x, and since these angles are the same, 60, 60, 60, before we cut it in half, that means that this side here and the other side will be the same, and so we know that it's an altitude as well as a bisector, which means now the short side, which has been cut off by the bisector, will be length of side x. And so if we wanted to find this altitude of this equilateral triangle, or the second side and the first, second, and third largest sides in this triangle, we can use Pythagoras again to calculate that. So what we'll do is we'll say, once again, we have a squared plus b squared equals c squared. And we know that our short side is x. Don't know the middle side. We know that the long side is 2x. So careful here. If you're going to square 2x squared, that's 2x times 2x rather than 2 times x times x. So 2x squared will be 4x squared, and we'll have x squared on the other side. And if we want to get b by itself, we just subtract x squared from both sides. And 4x squared minus a single x squared is going to give me 3x squared. And to get b by itself, we're just going to go ahead and square root both sides like we did with the 45, 45, 90, giving us that b is equal to x times the square root of 3. So that side right there is x times the square root of 3. Important thing to note here, this is a good way to calculate the area of an equilateral triangle because we now have both the base and the height. So big hint there for solving some of the more difficult questions on the test. Now we'll just finish off here with a couple of examples of applying these triangles to questions. So the first one here, we say Alice starts at her campsite, then walks 8 miles to the north, and then 6 miles east. How far away is she from her campsite now? So that 6 and 8 number there, we may recognize if we go 8 north and then 6 east. That sounds a whole lot like 3 times 2 and 4 times 2, or 5 times 2 for that distance. So that's just 10. And then for the second question here, I've just sketched out a regular hexagon where they say, what is the area of a regular hexagon with length of side 6 inches? So important thing to know with a regular hexagon is since it's regular, all the sides are the same. And you can kind of see here that we can just subdivide this up into 6 equilateral triangles. And then it's just as easy as calculating the area of a single equilateral triangle and then multiplying that by 6 to get to the area of the hexagon. So going back to what we just did a moment ago with the 30, 60, 90 triangle, if this length of side here is 6, that means that the short side is 3, and the middle side is then 3 root 3, and the area of a triangle is 1/2 times the base times the height, and so that's just going to be 1/2 times 6 times 3 root 3, and we can just simplify the half and the 6 to be 3, giving us 9 root 3 for the area of one of these equilateral triangles, and 9 times 6 is just 54 root 3. So here, just a very effective way to calculate the area of a shape that you may not believe you have the proper tools to calculate on face value. Okay, that's it for this video. If you found this material helpful, please consider liking, sharing, and subscribing to Quad Education. Thank you for watching, and I hope you have a great day.